Okay, so thank you everyone for coming. My name is Holger. Today I would like to talk about how we teach cars to see at scale at Motional. So yeah, what I'll be talking about, quick intro about myself, then what is our company all about, Motional, some public data sets that we published, nuScenes was already mentioned, some papers that we published a while ago, kind of our most well-known works. Then I would like to talk a bit more in general about data-driven development, and in the end, I will end with talking about data annotation and quality requirements there. Okay, so quick intro about myself. I'm from Germany, did a bachelor's and master's at KIT in Karlsruhe, did a PhD in Scotland at the University of Edinburgh, and was an academic guest at ETH Zurich and EPFL in Lausanne. And topics that I worked on, I started out with speech recognition and activity recognition, but eventually I turned to computer vision, especially semantic segmentation and detection. And yeah, the topics of my PhD were methods for weakly, semi, and fully supervised semantic segmentation and detection. And in particularly, I created a lot of data sets. The most well-known are Coco Stuff and nuScenes, which we'll talk about later. Okay. Now I would like to talk a bit about the company that I work for. So the company is called Motional. Motional is a joint venture of Aptiv, which is a very big automotive supplier, and Hyundai, which you all know, the OEM. And both of them contributed roughly the same amount of value, around 2 billion each, to this new company. And the name is Motional. And you can see that we have a long history of milestones for autonomous driving. So we were founded out of two startups, basically spin-offs from MIT and Carnegie Mellon. So these spin-offs are called nuTonomy and Automatica. And then basically these were merged together into one company. Yeah, we were acquired by Aptiv and then eventually became this joint venture. We were the first company to perform a US cross-country drive back in 2015. In 2016, we were the first company to provide a public autonomous vehicle demo in Singapore. It was also a world first. We continued in Boston, and then in 2018, we set up a large deployment, a fleet of between 50 and 100 vehicles in Las Vegas. And the way it works is that you can basically use your Lyft app to call our vehicles, our autonomous vehicles, and they will come and pick you up. And yeah, some other milestones. 2019, we released nuScenes. We published some safety white papers. We expanded into Shanghai. We achieved a milestone, 70,000 commercial rides. And then, yeah, as I already mentioned, we created this joint venture between Aptiv and Hyundai, which is Motional. Here you can see some of our offices. So we have a lot of offices in the US, in Las Vegas, Santa Monica, Pittsburgh, and Boston. And then we have offices in Singapore, where I'm based, and in Seoul. All right. This is a little teaser video for our new brand. I would just like to show you that. Let's see if we can hear the sound.
We can't hear.
You cannot hear the sound? Okay,
No.
let's wait 1 second. Maybe we can share that. Share the sound.
When you press the share screen, there's like a checkbox next to it.
Yeah. I believe now it should work.
It's power.
Yep. Yes.
It's opportunity. It's pushing for what moves you. When people change the world, they call it a movement. Movement is power. It's opportunity. It's pushing forward, determined to create a better future. It's imagining the impossible, then making it real. It's what drives us. We are Motional, and we're making driverless vehicles a reality. The future of transportation starts now. We're focused on you, your choice, your safety, your community. We believe getting places reliably and confidently is your right. That's why Motional is changing how the world moves. Everyone's journey is different. And no matter where your journey takes you, we'll get you there. Motional. You move the world, we move you.
Okay. So as I said, this was a video released for our brand launch, which was last year during COVID. So it was, of course, a difficult time, but it's exciting to have this new brand. And here's one more video, which is from Las Vegas. So of course, COVID also affected our operations, but after a while, we were back with our fleet in Las Vegas. So this is a video to celebrate the milestone of being back on the strip in Las Vegas. This is our garage in Las Vegas. And this is exactly this partnership that I talked about between Lyft and Motional. All right. Now let's talk about some algorithms. So one of the first papers that we published was PointPillars. PointPillars is a LiDAR-based 3D object detection method. So the input is a LiDAR point cloud, and the output is these cuboids that you see here in different colors. The colors corresponding to the labels. So you see cars, pedestrians, bicycles, etc. And the way this method works is that it organizes the point cloud in vertical pillars, and then it learns the feature representation inside each of these pillars, which is a standard point net. Then it stacks these feature representations in a pseudo image, and then that is passed to a backbone and a detection head, which outputs these detections. And that's a very interesting approach because it's very fast. Since we don't operate on every single point, we just aggregate them in this point net. And then it can use all of the standard tricks that image-based CNNs use. So we can use our standard backbone that we like, ResNet or something. And we can also use standard detection methods like SSD, which is very popular and, of course, very fast, at least at the time. Let's see how that performs. So here we see the leading method at that time. We see inference speed on the x-axis and mean average position on the y-axis. And we can see that PointPillars really outperforms all of these methods by between 2 and 4x the speed, and also achieves as good or better performance than the leading methods like when we published this paper. And what's really impressive, I find, is that we achieve up to 100 Hertz inference time. So that's super fast. You may, of course, ask, why do we need 100 Hertz inference time when the LiDAR only records at 20 Hertz? But if you assume that we have 5 or maybe 10 different LiDARs on the car, then with 5 LiDARs, we would need that to be in real time. So this was the first method that kind of unlocked this real-time performance. Okay, the next method I would like to talk about is called point painting. Point painting is a fusion method for LiDAR and camera. And the way it works is that it operates sequential, and it combines the 3D LiDAR detections, for example, from PointPillars, and image semantic segmentation. And we will see that this improves the 3D detection performance across all classes, data sets that we tested, and different detection methods. So here is the schema of how that works. Step 1 is we take the image, we perform semantic segmentation. That means every pixel is classified with one of several classes, like cars and bicycles. In parallel, we also have the LiDAR point cloud in the top left corner. And then we perform point painting, which really just means we reproject those points from the image onto the LiDAR point cloud. And then we concatenate the LiDAR features with the scores from the semantic segmentation network. And if you think of this as hard labels, then it's painting, because you're assigning one label to each point. But in practice, it's probably cleverer to work with soft labels. Yeah. And then the next step is just use whatever standard LiDAR detector that you want. for example, PointPillars or PointRCNN, and then you get significantly better detections than if you just use that detection method without point painting. Okay, here are some results on the famous Kitty dataset, the val set to be accurate. And we tried different methods, which are PointPillars, VoxelNet, and PointRCNN. And we can see that on each of these methods, if we use the painted version of that, we achieve significant improvements between 1 and 4%, which is, of course, very nice. And then if we look at the test set, again, many different methods here compared. We chose the best method at the time, PointRCNN, and applied point painting on top of that, and we get another 2.94% improvement, which resulted in state-of-the-art results. So that's very neat. And of course, if you consider that an autonomous vehicle may already have the LiDAR-based detector and the camera-based detector or segmentation method, then it is basically straightforward. It's for free to do point painting. Okay, this is another paper from our behavior modeling team, which is called CoverNet. And what it does is it's a method for trajectory prediction using trajectory sets. So trajectory prediction means that for every agent, you figure out where they're going to be up to 6 seconds into the future. And the way it works is that it generates sets that are designed to cover the dynamically feasible vehicle trajectories. We will see that in a second. And it outperforms methods based on regression and ordinal regression. So here's an overview of the network architecture. The input is actually an image with 3 channels, RGB. And that image represents the local environment around our car. We see the lanes, we see the sidewalks, crosswalks, drivable surface, etc. And we also see all the agents, including their history. So you can see the different shadings there kind of indicate that a certain car was coming from here. This is the input that we give to the network. And then we, of course, also give the states of the agents, such as speed, acceleration, yaw rate. And then in the first step, we generate the feasible trajectories for this state, which could look like this if you assume that the agent is here. And then we essentially classify them and compute the probabilities for each of these trajectories. And then we pick the highest scoring ones. And those will be our most likely trajectories. And the results were very good at that time. So we evaluated this on the nuScenes dataset on the 6-second prediction horizon. The metric here is hit rate, which is defined over the top K prediction and then within 2 meters. That's 1 if you hit that object within 2 meters with the top K predictions, or 0 otherwise. And if we see here, we have CoverNet, 3 different versions of it, and then a number of baselines and oracle methods. And we can see that CoverNet really achieves state-of-the-art performance better than the baselines and other state-of-the-art methods over various different numbers of K. Okay, now I would like to talk a bit about data. So this is actually one of my main projects, or was my main project in the first year. It's called nuScenes, and it's a multimodal data set for autonomous driving. You can see a sample here at the top right corner. So we have radar, LiDAR, and camera data. We have map data as well with 11 semantic labels. We have textual descriptions of a scene, something like pedestrian with pet, bicycle, car makes a U-turn, lane change, and pedestrians crossing a crosswalk. And then the most important thing is for each of the 1,000 scenes in this data set, we have every single object annotated at 2 Hz with these cuboids that you see up here. And of course, we have information such as categories, attributes, such as are they moving, are they standing, etc. It's a high quality data set with synced sensors, properly calibrated, and also localized. Of course, that's important. If you want to work with a map, you need to know where you are on that map. Yeah, it's, as I said, fully annotated in 3D, and it's free for research. So you can go to this homepage, nuScenes.org, and download the dataset. you will just need a big hard drive for that. Okay, and nuScenes is quite unique in terms of its diversity. We really went through every single one of these 1,000 scenes and made sure to select only very interesting maneuvers and also a high focus on rare classes. So especially bicycles, but then also construction vehicles, construction workers, a lot of different fine-grained classes. We have 4 diverse locations from Boston and Singapore in this data set. And because of that, of course, we have left-hand versus right-hand driving, which is quite interesting, especially for behavior modeling. Then we have different vehicle types and vegetation types, of course, between Asia and the US. And additionally, we also have nighttime and rainy data. This was also something new, which no other data set had at that time. So you can kind of see how well your method would perform at night and in rain. Yeah, here's another layout of our car with the 6 cameras, 1 top LiDAR, IMU, GPS, and then 5 radars. And what's also new is that this was the first 360-degree dataset, large dataset. Kitty, for example, only looks forward for the camera and the annotations. And then it's also the first dataset with radar data. So that was also important. Okay, here you see an overview of a lot of datasets that came before us, or these 2 sections are before us. This 3rd section is datasets that were published after ours. And you can see that compared to anything before, our dataset is much bigger. If we look at, for example, the number of LiDAR point clouds or the number of annotated boxes. But since then, of course, other datasets were released. We have Argo, Lyft, Waymo, A-Star, and Audi. And but it's interesting to see that even now, Waymo is the only dataset which is our size. I think lately they released some extensions, so slightly bigger now, but it's still similar order of magnitude. It's just worth noticing that they use 10 Hertz annotations, whereas we use 2 Hertz annotations. So it's kind of the same thing, but just inflated by factor 5. Yeah, they don't have a map. So especially you can see here, we have very fine-grained classes, 23 classes, so that makes it quite special. Okay. So now the question here is, in some of the experiments we did for that paper, do we really need larger data sets? Is Kitty not enough? And we did some experiments where we just varied the amount of training data on nuScenes. These are 3 methods, basically 2 image-based methods, and then 1 LiDAR-based method, PointPillars. And we can see how the performance increases, of course, with more training data. This amount of training data here corresponds to Kitty. And if we compare this point here with 100% data, then we will see that we achieve about 70% relative improvement with PointPillars on nuScenes amount of data compared to Kitty amount of data. So you see, it's really important to have these large data sets. And of course, we will need even larger data sets in nuScenes. Okay, so we released this data set, and it was an astonishing success. A lot of people downloaded this. I think 10,000 people signed up to download it. Was also cited 550 times. So we thought about what else can we do? And a lot of, especially companies, contacted us saying they would like to work more with 2D data. So we created a very similar data set from the same domain, which is called nuImages, which contains 100,000 images with 800,000 2D boxes and masks. And additionally, it also contains the past and future images and ego poses. So it's essentially a data set with 100,000 video clips and localized on the map. So that's a very interesting large-scale image data set with boxes and masks. And then another project was nuScenes LiDAR-sec. Here, what we did was basically we took nuScenes and annotated every single keyframe, 40,000 keyframes, with point-level semantic labels. So for 1.1 billion points, we annotated them with a label saying this is a car, this is a road, sidewalk, etc. And I think this is very important LiDAR segmentation. It has received a lot of attention in the last year, but I think there's still it should still be more important. I think it's important to go beyond the bounding box. 3D bounding box is a very coarse approximation. We should go beyond that, more fine grain, and then also focus on stuff classes. So the road, the sidewalk, the building, all of them are important for the problem of autonomous driving.
I have a question.
Yes.
Regarding the annotations, what was this is large data sets. How did you do that process?
So all of these data sets are 100% human annotated. So there's no tricks with pseudo labeling or something like that.
Mm-hmm.
All of them are human annotated.
Well, there was 800,000 images humanly annotated.
Yes. And the
with 2D boxes. Okay.
Yeah, and this
how
is
many?
1.1 billion points also human annotated.
Well, can you elaborate?
So of course we do work with external partners. We don't have hundreds of people sitting in our offices just annotating these, but it's a fairly big workforce, of course, and good tooling that is needed to annotate these large data sets.
Another question, if it's okay to ask, I don't know, but partly because of curiosity, what is the price to annotate this size of data set?
That's difficult. I would say for nuScenes, maybe one scene could be roughly around $100. So you would be talking about very roughly $100,000 for just nuScenes.
Mm-hmm.
And then this type of annotation is a bit more pricey, maybe twice as much. And for nuImages, it's very difficult. It's roughly between $1 and $3 per image per task.
Per task.
Yeah. So if one task is 2D bounding box, another is instant segmentation, and the third is semantic segmentation, then you would have 3 tasks per image.
That's about a $2 million annotated data set then.
Yeah, maybe something like that. This is rough numbers, but something like that order of magnitude.
But Peter, if you're interested in annotations, we can also give a talk for you if you want at some point.
Yeah, let's talk after this talk for sure. If you could reach out to me, I just don't have your contact right now, so
I'll do that.
Mm-hmm.
Okay. Yeah, so this is a little demo from nuScenes LiDAR-Sec. I'll just increase the quality here. So as I already described, what we can see here is every single LiDAR point labeled with a semantic label. You can see this teal corresponds to the drivable surface. Green is the grass. The other green color is vegetation. We have buildings. We have different kinds of vehicles, other ground classes. Yeah, let's take a look at how that looks. So you can see this in really great detail, even far away objects there, for example, all the pedestrians. So it's been very detailed work for us to even just correct all of these annotations, like QA them. And of course, annotating them is even more work. Okay. And of course, you can download this data and then experiment yourself, train a neural network to predict these labels. Okay. Then what we did with the nuScenes dataset was we conducted a number of different challenges from 3D object detection, 3D tracking, prediction, similar to what I showed you before, and the last one, LiDAR segmentation. So that's on nuScenes LiDAR-Sec, leveraging these point level labels. And we did organize these challenges once or twice per year at all the major computer vision conferences, CPR, ICRA, NIPS, and others. And I just want to show you this plot here. This is from the detection challenge. You can see the date of the submission at the x-axis, and then the performance is our own metric called the nuScenes detection score. We will talk about that in a second. And it's quite interesting to see. So PointPillars that I presented to you is already a bit old. It's from early 2019, roughly. Or maybe late 2018, even CVPR, that achieved state-of-the-art performance back then. Then we organized a detection challenge, and there was a huge boost here. This was a submission from MACV, which is called CBGS. Then this is our PointPainting fusion paper that I talked to you about. And then the next detection challenge the next year, again, huge increase in performance to NOAA CV Lab. So there's, from the NOAA lab. And the last challenge now was center point V2, again, achieving a big improvement in performance. So that's super impressive to see that in 20 months, we saw an increase in performance of MAP of 36.6%. So that's huge. That means, we've almost doubled the performance since then. And what's also interesting is if you compare the blue stars and the red diamonds here, you will see that all of the top performing methods are LiDAR or fusion. So I've just put, if it contains LiDAR. So I guess that's bad news for Tesla probably, but I'll leave you to discuss that. That monocular image methods, based methods are not performing as good as LiDAR methods so far. Okay, now I would like to talk a bit about data-driven development. So what does data-driven development mean? It means we have our drive logs, we randomly sample some data from them. Could be, for nuScenes, it's in the end only 5.5 hours, but it comes from maybe 100 hours of driving data. Then we manually annotate that data, really high quality annotations that you saw, very tedious, very slow. And then we train our ML algorithm to learn to detect these objects. So this is the standard way that data-driven development works. And if you want better performance, it's very easy, basically 3 steps. Step A, you draw more samples. Step B, you annotate more data. And step C, you train a new model. And whenever your boss wants a better model, you just follow these steps and you get your better model. But of course, the returns are a bit diminishing there as we increase the amount of data. And probably there are also more clever things that we can do. So one thing, for example, that we can do is use the neural network that we trained, the ML algorithm, to do active sampling or active learning rather than random sampling. That is pretty obvious. So you should always filter your raw data by some criteria. For example, what's really important for us has been since day one is just to run your neural network on the data and filter for bicycles, because bicycles are a really difficult class. That is a really easy way to increase your performance. Second step is rather than human annotation, you should try some form of automated annotation. Of course, the performance will be slightly lower, but if you can do that on a really large scale, you should still achieve better performance for less money. And then finally, you can also use the network to refine the annotations that you already have in your database. So we do that periodically, that we compute the loss of our model on our annotated data. We sort the whole data set by the loss, and then we just manually review all the top loss images. And that's a very good method to kind of clean up your data set, because there will always be human errors that you can at least reduce to some extent with this approach. Okay, so now I've talked a bit about active sampling and more generally active learning. So active learning means that we have an unlabeled data set. No, let's start the other way around. Essentially, we have a machine learning model that determines which data should be labeled by a human. It's called the oracle here, added to the training set, and then used to improve the machine learning model. And there are many ways to do this. Some techniques to flag interesting data for annotation are disagreement between different models. So you take different models, form an ensemble between them, and you compare where they disagree, and that's probably the ones where you have high uncertainty. Another approach is compute the disagreement between the same model with different randomness. In some sense, that's also a different model, but it's just different randomness. It's using dropout. Another method is the disagreement between the same model from different viewpoints. That's a very interesting recent method that, of course, depends on the data, but looks at the same scene from different viewpoints, mostly in indoor 3D scene reconstruction. Another method is compute the disagreement between the same model across time. So you're basically leveraging the temporal coherence. That's something that we are also very interested in. Essentially, you know that if you detected something in the first frame and in the third frame, then it's probably also good, and you don't detect it in the second frame, and that's probably going to be an error. And you can mine for that, and you can use that to annotate those samples. And the last one is a very interesting approach called loss prediction. So basically here the network gets another output, which is the predicted loss of that network on an image. So it's kind of guessing how confident it is on an image. And then again, you can sort the images by this uncertainty. And then you know which images to annotate. Okay. Something else is metrics. Metrics, of course, are very important, not just because we are designing data sets, and if you create these challenges, you also need metrics for them, but also for active learning, for example. We need to have good metrics to even decide what data helps us, and then, of course, in the end, to measure the performance of our AVs, that we need to have reliable metrics, which should go, of course, beyond perception. But here I'm mostly focusing on perception and planning. So the classical metrics are precision and recall-based metrics, such as MAP, mean average precision, which is, of course, the integral over the recall precision curve and then averaged over the classes. These have been used for many years and are very well established. Some more novel domain-specific metrics are, for example, the main average position weighted by heading, which is what Waymo uses in their open dataset paper. So that gives a higher weight to the objects in front of us. And then we introduced this metric called the nuisance detection score, NDS, which is really just a weighted sum of the MAP and then the translation, scale, orientation, attribute, and velocity arrows. And the reason why we did that is because we really wanted to make sure that it's not just about MAP, but that all of these other aspects are also taken into account. Especially attribute and velocity was something that were never taken into account. And it's really important for us in an autonomous vehicle to estimate the velocity reliable. So that's why we introduced this metric, which kind of compounds all of these factors into one. And something else is the neural planning metrics. That's a very interesting idea. So basically, there was a paper by NVIDIA called PKL metric. And what they do is they use the predictions of our object detector, and then they compare how similar is the planned route using these predictions to the real route. So you're kind of comparing where you planned to go to where you actually went a posteriori. And that's why it's KL divergence between those two. And we also recently did some like a study of PKL on nuScenes, kind of a large-scale study with all the different methods. You can take a look at that. We also added this metrics to our nuScenes detection leaderboard. So it's kind of interesting to see where it correlates with MAP and where it disagrees a bit in some cases. Okay, and then of course, you don't just need algorithms and data, you also need good tools, good infrastructure to work with these large data sets. So one company that we've partnered with for like, open source purposes was SiaSearch. And what we did is we gave them our nuScenes data set and they indexed that. You can see it here, you can search for nuScenes and then you get all the 1,000 scenes. And of course, they indexed that by hundreds of different search criteria. You can see here the distribution, night data, rain data, map distribution, class distribution, different maneuvers. So that's pretty interesting to have these kind of dashboards and just navigate your data and figure out, are there any domain shifts between maybe train, val, test set? How do different cities differ? Are there many more bicycles in one city than in another, for example? So that's really interesting to have these tools. And you can also go to their homepage and log in and try out the nuScenes dataset for free. Okay, and now I would like to talk a bit about data annotation. In general, I think a very important takeaway from this talk should be that algorithms can be changed. You can get another neural network to do object detection for you, but the data is there to stay. So in academia, we don't care much about the data. We just take whatever data set is out there. We run our model on that, and we hope for good results. But in a company, you are responsible for the data. And any decision, any bad decision will follow you for the next many years. So some important decisions are, for example, should you do modal or amodal annotation? To explain what that means, modal means you only annotate the visible parts of an object. Amodal means you annotate everything, even if you don't see it, if it's occluded. So that's particularly relevant for boxes, either in 2D or in 3D. So in 3D, I believe pretty much all data sets go for amodal detection, basically meaning that they outline the entire extent of a vehicle, even if you don't see the front, kind of guessing where it could be. Whereas in 2D, most of the data sets actually go for modal, like Coco and so on, which means you only put the box around the visible parts. So that's a very important decision. Of course, it will impact your entire stack. So you should think about that early on. Another question is, of course, what should you annotate? There's so many different types of annotations out there and many different companies offering different ideas and solutions. So for example, 3D boxes, 2D boxes, instance masks, semantic segmentation background masks, point level labels, map annotations. There are really a lot of different ideas out there. Another question is, do you annotate objects like a bicycle and the rider? Do you annotate them as one, or do you annotate them as two objects? Maybe even modeling the relationship between them. Because in theory, of course, the rider could get off the bicycle and walk away from it, which would probably be a problem to most detection systems or trackers. So that's also a very interesting decision. For nuScenes, we decided to have those together. And I think that's actually a very good idea, because otherwise it's very difficult to make this association between your bike and your rider. Is it still on the bike or is it already somewhere else? If you always assume it's just one object, that makes many things easier. Another question is, how do we deal with missing labels? So assume we have 30 classes in nuScenes, something like that. What do we do with other classes that are not in our taxonomy? And one thing that I always like to do is to just have an other class. So we would have something like other vehicle, which just covers any kind of vehicle that you didn't think about. And you can even have a high-level other class, which covers everything that's not even a vehicle or a human or such. So that's kind of relevant for the problem of generic object detection, making sure that we're not missing anything out there, which we forgot to annotate because we don't have it in our taxonomy. And the last question here is, what quality of annotations do we need? And I will show something about some small study about that question in a second. Here's just one more kind of case study I want to show you. This was from 4 or 5 years ago, where we trained an image detector on a small data set, and it had a solid MAP and did well on small objects. But then, so standard images from training set would look like this. But then we got some testing images like this, and none of the very close, tall pedestrians here would be detected. And of course, we looked at the data, and we saw that there's essentially no data or almost no data above 400 pixels. So these are probably 800 pixels, so they're much, much taller than any of the pedestrians we had in our data set. And that's, of course, not a surprise, right? The neural network is really good at learning the data that you give it, but if it hasn't seen something like that, it won't generalize to that, by default at least. Okay, and this is a small study of what is the impact of annotation errors. So the reason is that, of course, we annotate a lot of data, we spend a lot of money, we have very high quality standards, but the question is that really necessary, this high standard, or are we just kind of exaggerating? And what we did here is we simulated different types of errors by corrupting the ground truth annotations that we had in our data sets. Each error is controlled by one variable to make it easy, and we can kind of increase the amount of error and see how the performance deteriorates. And then we train a LiDAR-based 3D object detector and an image-based 2D object detector on these corrupted annotations and see how the performance deteriorates. Here are the different types of errors that we introduce. There are category errors, where we basically have randomly flipped the box label to another class. Translation errors, where we randomly translate the box. Scaling errors, false positive errors, where we randomly add boxes, and false negative errors, where we randomly remove boxes. And yeah, here you see the metric. It's pretty obvious. So for category, it's the error probability. So with 10% chance, we are flipping the label. These two use the reduction in IOU as a metric, and these simply use the relative change in the number of boxes. Okay, so let's look at how that looks. First, this is for category errors. We see again on the x-axis the probability of changing the class label. So this means here, it's hard to see, but this means 10% chance that we flip the label for any box. So on average, 10% of the data will have the wrong label then. This is normalized MAP, so it always starts from 100%. And now we can see how these curves kind of deteriorate as we introduce more noise, which is kind of how we model worse quality annotations. And we can see that this looks pretty similar for the image-based method and the LiDAR-based method. 10% error has basically no impact on quality, but then it gradually goes down. If we look at, we have 90% normalized MAP at 25% category error rate. So that's pretty interesting. If 90% is acceptable for you compared to our baseline, then you can have 1/4 of the labels wrong, and it would still be good enough. The next is translation errors. This looks a bit different because the image-based detector is much more error-prone here. We see the IOU drop on the x-axis, so the reduction in intersection over unit, which is kind of the tightness of the box fit. And we see again in the beginning, the translation errors have very little impact. So if we reduce IOU by 0.1, 0.15, that has very little impact. But then if we go beyond 0.2 or 2.5, there's a huge impact on the image-based method. So if we again look at this 90% normalized MAP threshold, we would have 25% lower IOU for image for the LiDAR-based method and 42 for the image-based method. Sorry, the other way around. So this is really interesting to see that LiDAR is pretty robust to these translation errors. Next one is scaling error, which looks very similar. If I compare that again, it's almost same curve, just that the scaling error stays up here at almost 100% a bit longer. So with the scaling error, we can afford 28% lower IOU for image and 50% lower IOU for LiDAR. And that's quite impressive. That means that the scaling error is really, the scaling is not so important.
I have a question about this. So if you add in half of the annotations are errors, it almost doesn't lower your accuracy. It doesn't sound intuitive.
So this one is here, the x-axis is IOU reduction.
Yeah.
So I guess you know IOU, right? Intersection over union between two boxes.
Yeah.
This means we modify the ground truth, and then we compare to the previous ground truth, and then we compute the IOU between those pairs. And then we just measure this is 20% less intersection over union. So it's not a probability, it's just how far off they are. So if you don't work with IOU very often, it's of course not very intuitive, these numbers. Maybe then this metric here for category error is more meaningful to you. Probability of changing the label, this is very intuitive, right?
Yeah.
Yeah. The IOU drop, I agree, is a bit harder to understand. But one important thing is that most of the challenges go somewhere between 0.5 and 0.9 or so IUU threshold. So that kind of gives you a feeling for what quality they require for a true positive, basically.
And the IOU, do you change the size of the bounding box, or you just change the position? In scaling, you probably change the size, but how much do you change it?
Yes, so it is actually following, it's a bit more complex, the study that we did. It is following a Gaussian distribution, I believe, for width, length, and height, and then randomly sampling from that, and then rescaling the box according to that.
Ah, okay.
So the exact details are a bit more tricky, but the outcome is that if you reduce the IUU by this much, you will get this much decrease in MAP.
Yeah, it's a bit of problematic metrics because it doesn't tell us a lot about what was the difference in sizes, not only in position, because maybe position, the scale remains the same.
Yes. So each of them is a separate study, right? So the translation error is one study and the scale error is an independent study.
Yeah.
Yeah. Of course, in the real world, you would have all of these together, which is a bit more difficult to model then.
Mm-hmm. I have a follow-up question, but maybe after we finish this part.
Okay. Yeah. The last two are false positive errors. So this is again interesting. LiDAR again very robust to small amount of false positives, whereas the image-based method already drops significantly after 4% of the boxes being wrong, or 4% more or less more boxes in this case. And we achieve the 90% normalized MAP at only 6% for image. And yeah, for LiDAR, it's hard to tell from this data. Probably should have made the graph a bit longer. Okay. And false negative errors also look similar. Image-based method, as always, drops significantly already here at 90% normalized MAP. We achieve at 28% change in the number of boxes. And for LiDAR, it's 60%. So again, similar picture that LiDAR is much more robust. And this is actually quite impressive, right? You can basically take away 60% of the boxes and like just forget to annotate them, and you still get 90% of the quality. Of course, that depends a lot on the detector that we use and the loss function in your detector. So other detectors may use every single box, and then it will probably end up being a different result. But we use SSD like paradigm here. Yeah. Okay, and then as a summary, so LiDAR-based 3D detectors are seem to be much more robust to annotation errors than these image-based 2D detector that I showed before. And we can drastically reduce the quality and therefore, of course, increase the quantity. And here I've kind of plotted this trade-off between quality and quantity. This is kind of the Pareto frontier where we have the same cost. So it's just abstract numbers, but I'm assuming that along this frontier here, we have the same cost. So we can either go for high quantity or high quality. But then what's interesting to see as an analog to what we saw before, here it's fairly constant. There's not a huge decline in quality as we increase the quantity. So these are the kind of sweet spots that we're looking for, where we have very little decrease in quality, but it's much cheaper, much faster, and therefore we can annotate much larger quantities. So that's probably what we should be looking for. Okay. As a conclusion, algorithms are essential, and we require really good public benchmarks so we can compare our methods. Data is essential, and we should share it and standardize it. Again, otherwise we cannot compare to other methods. Data-driven development provides a path to better models. Metrics are also essential because we need to solve for the right problem. If you have the wrong metric, you're not solving for the right problem. And automating this data-driven development cycle is a really important research direction that we and many other companies are still working on. And data decisions and quality have a really long-lasting impact. So at least if you work in a company or in your own project, you should think very carefully about how you design your data. Okay, that is everything. I would like to thank you very much. Also like to thank all my co-authors and colleagues. If you're interested in working with us or an internship, you can go to our careers page. Otherwise, you can always reach out to me. Or if you just want to do some research, you can go to nuScenes.org and download the dataset. Okay, if you have any questions, feel free to ask afterwards.
Yes, we have. we have on chat. I have some. So if we can go back to the slide when you mentioned what parts you need to think about when you're planning how to annotate the data set. I think it's about 2 slides.
I guess
Yeah, this one.
Data-driven.
No, a bit forward. Maybe 2 slides forward. Yeah, a bit more. Yeah, here. No.
So this one, okay. I think there's a bit of a lag. That's why.
Okay. Sorry. So there was the one that with this, like, I remember the example of should you annotate the bicycles and the person separately? It was one of the points there.
Yeah, I think that was here in the next section here.
Yeah. So about the modal versus, so I want to, the workflow and the work process, the thought process is interesting for anybody who's working with end-to-end machine learning project or research, right? So we mentioned the modal versus amodal. So the 3D, you want to work with what you don't see also, and 2D data sets you don't have to maybe. But let's ask that annotate bike and rider as 1 or 2 objects. So in your research, how did you answer this question, or did you even answer it?
I mean, ideally, you would annotate 1 million images for each and then compare what works better.
But you have a limited time and money.
Yes, and you want to get running soon, I guess. So it doesn't work. You look around with what other people do. And then you just think about, do we really want to model these relationships between bike and rider? There are maybe a few special cases where you do want to do that. So one is articulated objects like a semi-truck, which has a front and a trailer in the back. And when they move around the corner, the front will move independently of the back, or kind of independently. So there you may actually want to model that as 2 cuboids with some relation between them. But so, I think in this case, for bike and rider, you have very little gain from doing that.
So the question comes, how can you maybe interpolate into the future what other annotations you will require when you're doing your next test of the algorithm, the next one? Like, how can you prepare and say, okay, let's say in the bicycle and person example, not so interesting because they're always connected. So it could be 1 object. And I know this even though I still haven't started testing the future algorithms. Maybe what is like, if it's a bit of a hard question because it's partly intuitive answer, but still, if you can break down the intuition into parts, how would you do it if it's possible at all?
So the question was, how do we prepare for the future, basically, our taxonomy, right? Yeah, I think so. Even we still get surprised. In a company with 1,000 people, there will always be different requirements, different needs. So things change very quickly. But I think some ideas to prepare for the future are, you should probably arrange your taxonomy hierarchically. So you start out with, can have one abstract root node, but then below that you probably have vehicles, pedestrians, other objects, and then all the background classes. That could be one way to start. And then you should, iteratively add more detail to them. So you can have trucks, and below this trucks, you can have pickup trucks, semi-trucks, and trailers, or something like that. So little by little, you should add more complexity afterwards. This way, you are kind of future-proof. You can even, if you already labeled high-level trucks or vehicles, you can go back and just change the label to the subclass. If you thought of that in the first place, then it's easy. If you just did not annotate those classes, then you need to look at every single image again and fix those, which will take a lot of time.
So maybe an idea here is to not prepare everything in advance, but do prepare the framework to change the annotation easily when you need to.
Yeah, so hierarchy is a very important one, I believe. Kind of refining that. And then the other idea was with the other class, to make sure you really cover everything, even if you don't know yet what it's going to be, just to make sure you cover anything unseen. or unforeseen with your taxonomy.
Cool. Another question about, you mentioned your nuScenes detection score, which you, so if you can maybe elaborate a bit more. I know it's maybe a bit technical, but still, this is a technical audience. So if we can touch a bit more, what does it mean?
Yes, so it's a weighted sum of MAP, mean average position, which is the standard metric in all of these challenges, and then 5 other metrics, which are all true positive metrics. So only on the match boxes we compute these. And those metrics are the translation error, scale error, orientation error, attribute, and velocity error. And they're all independent. We also actually list them independently in our leaderboard. And then just for this metric, we compute the weighted sum of those. So it's really nice to see. Sorry?
Yeah, go ahead.
Yeah, so it's really nice to see on a leaderboard, okay, this method has the highest MAP, but they're actually not doing well on velocities because they're only using one LiDAR sweep and not like past LiDAR data as well. And from one snapshot of the world, it's very difficult to estimate if you're going fast or slow. But if you have the past data as well, then it's much easier to compute the velocities. So you can do this more detailed analysis of a method.
And how do you weight that sum? How do you put a weight on each part?
In our case, it's very easy. We just said 50% MAP because that's an established metric, and 10% for each of the others.
Okay.
Yeah, I guess it really depends on your use case. Yeah.
And also maybe I missed that, but what is attribute? What is that metric?
Yeah, so in addition to categories, we also have attributes in our dataset. They are simply for a vehicle, for example, is it stopped, parked, or moving? For pedestrian, is he standing, walking, sitting, lying? So it's different states that an object can take, and specific to the category.
Okay, nice. So that was it from me. I also have a question, which Uli also had, which is you actually touch about the point of using LiDAR or not using LiDAR, which is a whole discussion right now, right? And if you could elaborate more, what is, for people who maybe are a bit less aware also, what is the advantage of not using LiDAR? What is the advantage of, we've seen the advantage of using LiDAR, but maybe, highlight it a bit better, more, or like, and also, why do you think, what is the thought process that says, look, LiDAR should be the way to go?
Yeah, it's difficult. I don't want to go too much into what competitors are doing or even what we are doing, but in general, I think the main point against LiDAR is that it's very expensive. So until a few years ago, LiDARs used to be $100,000. Now they're maybe $10,000, and soon they will be $1,000 if they're solid state. So they're getting much cheaper. And of course, they are starting to be mass produced. So in the beginning, you had only spinning LiDARs, and after a few months or so, you need to do maintenance on these. So it's really moving parts that are not very robust. So you cannot roll them out in 10 million vehicles or something. That you would need a garage regularly to inspect your car. That wouldn't work, right? So far, LiDAR was kind of a prototype, not very robust, and that's why some companies say you shouldn't be using LiDAR. It's just too expensive and not worth it. Another argument is that humans don't use LiDAR, right? We just have 2 eyes, maybe ears, and that's everything that we use for navigating with a car in traffic. So if humans don't need it, why would an autonomous vehicle need it? And I guess the counter argument here is safety. You always want redundancy, right? So probably you should take radar, LiDAR, camera, ultrasound for very close distances, really anything that you can get your hands on, and combine them. And even if one of them either completely fails or doesn't operate well in rain, fog, sun glare, etc., then you should probably use the other, or some weighted combination of them, or something like this.
Mm-hmm.
So there are some interesting papers coming up where they really devised methods that if my detector completely fails, I still fall back on a baseline performance from another modality, which is in some sense also what our point painting was doing. Because if the semantic segmentation doesn't work, you fall back to the PointPillars performance, which was just LiDAR-based detector. It's kind of saying when there are no images or the images are corrupted or something, then the performance is the same as with only LiDAR. So robustness is very important for safety purposes, redundancy.
Mm-hmm. Good. Thank you for the answer. It's always a question that comes up often with people.
I guess there are many more aspects of this question. These were just a few.
Yeah, there's also a bit political, so you can't really touch everything there. But
yes.
But we're science people, and at least we get to say the science part. So we have a couple more questions about the presentation. Uli asked about that part with the automatic annotation. When we mentioned that maybe recognizing parts that should be annotated more or automatically. So is there a man in the loop to verify and correct the annotations?
That also exists. I'm also very interested in that topic. For example, Google has the Open Images dataset. And what they did was really they had an object detector which suggests bounding boxes. And then they have humans verify saying this is good or bad. It's a very interesting approach to get really large data sets, maybe not human level ground truth, but close to it for very little money. In our data set, it was all human annotated anyway, so we didn't need that.
Yeah, it's a benefit when you have a big operation. You can go for the quality more. Arun also asked, are there any ways to introduce dataset variability in the nuScenes dataset? For example, can I add rain or fog in the dataset and then see how my 2D and 3D object detectors are performing?
You could use, again, for example, generative adversarial network to modify the images. There are some cool GANs which add rain or fog or something to your images. But of course, it depends on the quality of your GAN, whether that looks realistic or not. In the end, I guess, if you really want to do that systematically, you need to go into simulation, which is, of course, something we also do on a very large scale to model, all of these corner cases. And you can even compare the performance between rainy day, foggy day, sunny day, and see where you're doing well and what's not working.
So do you use the simulations in combination with the real life data, or is it completely separate?
I guess it's always both, right? So probably the first thing, before you even go out with your autonomous vehicle and drive on a public road, you should probably first test it in simulation. Then, when you think it's safe there, you test it on a test track, and only then you should probably go on the public roads if everything is deemed safe. So you always need all of these. And as I said, there are just very different things that you can do. Nowadays, unfortunately, simulation doesn't look that realistic yet. It's not quite at the level of the best computer games, and even they don't look 100% realistic yet. But as it improves, it will become more and more important.
And we had here Marilyn asked, what do you think of bootstrapping method for training the LiDAR-based object detection model with less data set?
I guess the question is, what kind of bootstrapping method are we talking about?
Yeah.
So what we tried, for example, is with various external data sets. So you can start just ImageNet pre-training. That should always give you a little improvement. Although on our very big data sets, it doesn't actually give any improvements anymore, which kind of seems to indicate that our data sets are just relatively big. Then training with external data sets by these various other companies, or Kitty, we tried that, and for many of them, we don't see any improvement anymore. Again, our data sets are big, and then the taxonomies are slightly different. There are always subtle differences as to how they annotate. So at some point, And then, of course, the cities are also different. Most of these data sets are in Silicon Valley or San Francisco. And then if you want to transfer that to Boston or Singapore, it may not work so well. So it is good to work with external data, but it may not always work as well as you think. There was one interesting paper recently. It's called something like Train in Germany, Test in the US, which exactly has the scenario you start with Kitty, but now you want to use that in a different country. And what they do is very easy and works very well, is just adjust the boxes. Just say there's a systematic bias, you can measure that. US cars are 1 meter longer, something like that. So we just adjust the boxes by that, train again, and then you achieve much better performance.
You know what? It's another idea. Probably somebody's working on it, but take different data sets from the same domain, figure out the variability, predict the variability, let's say even, and then use that prediction in order to change your annotated data set and retrain your model or make it more robust, let's say.
I guess one thing is also simply using GANs to kind of account for this domain shift and adapt the images to look a bit different.
Yeah, but it's not as accurate as you'd want it to be many times, right? It puts random artifacts in the image. And Uli asked a clarification about the part when we talked about the robustness of checking the robustness of the LiDAR data and the model training accuracies. So he's asking why introducing errors such as class error, translation, etc. is, I'm not sure the question exactly, but I think he's asking why does it make the model more robust? Maybe a clarification again about that part.
I meant why the LiDAR is much more robust rather than the images. It's like...
That's a good question. So first of all, we are a bit comparing apples to oranges here because it's 2D versus 3D and then camera versus LiDAR. That's just one excuse here. But I think in general, in LiDAR, in the 3D world, if you, it's difficult to say. So one aspect is in LiDAR, you often would have like an entire parking lot with 100 different cars that you're all supposed to predict. Whereas in an image, often these are occluded. So you're kind of just predicting the first row of objects. And therefore, if those have errors, like those close by objects, they should be much more accurate. The faraway objects probably are not so important either. But in LiDAR, there's not so much prioritization. The cars are all 5 meters long or something. Whether they are 5 meters away or 50 meters away is not really being taken into account here. So there could be one other reason why LiDAR was more robust.
In this case, do you annotate the 2D bounding boxes as the estimated size of the object or the observed object?
Yeah, those were A-modal 2D bounding boxes. So it's the actual size.
Yeah, because in LiDAR, then you still annotate the expected size of the car, right? Which means that you by default have more uncertainty about where the vehicle actually is. So that might also be a difference that in the image you can exactly see the edges, or it's, I mean, up to, I don't know, 4 pixel precision or whatever, you can know where something is. Whereas in LiDAR, you're always guessing a bit where something is.
Yeah. I guess in general, also LiDAR data is very different from image data, right? LiDAR data is very sparse. In a big part of your scene, there's nothing. And then only you have certain clusters, essentially. So you just need to find those clusters and classify them. Whereas image data is dense. Every pixel has data and could potentially be an object. So that also leads to different statistics, especially when you introduce false positives or false negatives.
We have another question from Marlon. What do you think of the fusion-based object detection being more robust in the future? Although point painting shows the improvement, but the best detector seems not to be fusion based?
I do believe, if I look at the challenges, that the top methods are usually fusion based plus ensembles. Ensembles always help. So I do believe that the best detectors are fusion based. Therefore, I'm not sure how to understand the question. Would you like to repeat?
Marlon, are you able to explain it more or use the audio?
Actually, maybe I misunderstood something, because it seems like when I check the Kitty benchmark, it seems like the 3D LiDAR based method is not. I think most of the method of the best method is not fusion based on the Kitty benchmark. I'm not sure if other kind of like the benchmark show that like there's some kind of the fusion based method, it would be better. But it seems like the toppest one is always LiDAR based on the Kitty benchmark.
Yeah, actually, on these results, you are pretty much right, except for our result.
I think for this result, you just kind of capture. I'm not sure if you're just kind of capturing some of the method, and then you try to kind of using some pinpointing technique and then to try to see if there are any improvement. But it seems like for some other the top ones in the Kitty benchmark, I check on this and on the website, it seems like they are all LiDAR based.
Yeah, it's an interesting question. I think a lot of that is just kind of laziness, that most people just want to work on LiDAR. Adding the whole image-based part, fusion, is a bit complex. So it's more work. I think a lot of people want to keep it simple. But it's an interesting question. Yeah. I do think, though, that at least on the nuScenes dataset, fusion is currently better. But maybe it's just the submissions are just biased on different datasets.
Because I'm also kind of a bit confused sometimes why the fusion space is not the best one. When I check the Kitty benchmark in the official site, and we just get a kind. Maybe I lost a track or something, but I see it's just my impression. I just check the ranking. The top ones is always not fusion based at this moment. So yes.
Yeah. I guess it would be really interesting to just run this as we did here, right? Take all of the methods from the Kitty leaderboard, all of the LiDAR-based methods, and apply the fusion part and see if it always improves. Because then you would automatically know that fusion is always better, right? But maybe there are some baselines where the fusion part would actually not increase your performance anymore.
Okay, thank you for your opinion.
Yes.
For this.
Okay, other questions?
Any more? Yeah, let's see. We don't have any on the chat. I think good time to wrap up. Holger, really thank you for giving us this talk. I think I promised you when we were chatting that this would be an hour and a half, even though it's a shorter talk. So I'm happy that that it happened that as promised, let's say.
You were right.
Yeah. And again, everybody, we have more upcoming events. You can see everything on the meetup also. Feel free to join. And thanks everybody for the participation. And I will say bye and until next time.
Thank you. Thanks a lot. Bye, everybody.